Okay, cool. So hello, I'm Tim. I'm from the University of Cambridge. I'm part of the Turing.jl team. And we're going to be talking to you about work we've been doing in extending the functionality of Turing, which is a popular probabilistic programming language written in Julia, to extend it to be able to perform efficient inference on state space models. And so the main goal of this work was to try to provide a flexible, but I guess primarily an intuitive interface for state-of-the-art SSM inference algorithms, while also targeting near optimal, like theoretically optimal throughput.
And I'm Charles. I'm from the Federal Reserve Board of Governors, and so I have to have a quick disclosure here. The beliefs presented by the authors are not a reflection of the Federal Reserve Board or the greater Federal Reserve System. Now that that's out of the way, let's talk state-space models.
Cool. Let's see about that touch. Okay, so what is a state space model? So they're composed of two components. The first is some unobserved latent Markov chain, which is denoted X here. And we receive noisy measurements that we do observe, Y, and these only depend on the current state of the Markov chain. And so this entire model is governed by these three distributions, and these each can depend on the current time step, as well as some hyperparameters theta, which may be known or unknown. And so because of this structure, the joint density of all these x's and y's can be factorized into this neat little form. And this allows us to perform inference in a more efficient way than if we just had a general Bayesian model.
Yeah, so the sequential nature of the state space model yields this relatively intuitive expression of the posterior distribution with a class of algorithms called filters that can essentially be broken down iteratively into two steps, the prediction and the update. The prediction essentially takes the previous values of the previous distribution of states and propagates them forward either by the state space model or some abstract proposal, and the update step, which evaluates its correction and like how accurately it represents the observed value at time t, which, since this is an online algorithm, it's actually quite a bit more efficient than something like MCMC. Online, by the way, just essentially means it has a constant computational complexity at every time step of the state space model. And so this isn't something that you can kind of do like out of the box in like Stan or like Turing. And so this is essentially why we wanted to define this like module. And so in a fully modular setting, since the output of both the proposal and the update step are the proposal distribution as well as the filtered states or the filtered density, we want to work with distributional objects, something that we can take a sample from and evaluate its log likelihood, which makes it not only easier to encourage users to create their own callbacks at every iteration of the algorithm, but it also allows us to make more complicated like inference algorithms, something akin to like marginalized filters or array-black-hole-ized particle filter.
Yeah, so I guess as a case study of the flexibility that our interface provides, I want to talk a bit about this special class of Rao-Blackwellizable state space models. So these have a special form where those hidden latent dynamics can be decomposed into two subsets, X and Z, where once we've conditioned on the X, we have some given values of X. The remainder of the model, so the remainder of the latent state Z and the observations, those combine form a conditional submodel that has a special form that admits closed form analytic inference. So a common example of this that frequently comes up in tracking literature would be a model where you have various nonlinear dynamics on the outside, but then after conditioning on those, your position and velocity, as well as the measurements that you receive, have a linear Gaussian form, and so can be inferred using a closed-form Kalman filter. So to perform inference on this entire model, the usual technique is using what's called a Rao-Blackwellized particle filter. And the idea behind this is you take your usual particle filter and replace the single value of Z that you would have in each particle with an entire distribution of Z associated with the X in that particle. And so this, in a sense, marginalizes out all the variability in that Z, reducing the effective dimension of our problem and therefore reducing the variance of any estimates we would derive from inference. So this is a very powerful technique and can be applied in many settings, and yet we were quite surprised to find that there wasn't a general purpose implementation of this outside of like very specific hard-coded ones for certain research papers until now. And so because of this, I guess, distributional focus of our interface, it's actually very easy to define a general purpose Rao-Blackwise particle filter that can take any arbitrary submodel and any arbitrary closed form inference algorithm. And the way this works is that if we have our empirical particle distribution, which is going to contain many of these pink particles, each with a singular value for an x, an entire distribution for the z, a marginalized distribution. If we want to update this entire particle distribution, what we can do is simply pull out that marginalized state and dispatch to whatever inference algorithm, closed form inference algorithm, is appropriate for that type of marginalized state. So we can then take that updated or predicted state and put that back into the particle distribution. And when it comes to updating, because these distributions are proper sampleable objects, when we do that update step, we can obtain an incremental log likelihood that can be fed back into the general Rao-Blackwise particle filter algorithm, and that's used to update our log weights in the particle container. And so essentially what we've done here is completely decoupled the implementation details of that inner closed form inference algorithm from the general Rao-Blackwise particle filter. And the key thing worth noting here is that this process of doing these closed form updates on every single marginalized state over the various particles essentially boils down to performing linear algebraic operations on very large batches of typically quite small matrices. And so we've taken a lot of care to make sure that we've optimized that sort of operation as much as possible. So we have some benchmarks. And starting from just a vanilla CPU implementation, because we're working in Julia, it's very easy to leverage the powerful multiple dispatch system that it has to use specialized operations that can speed things up. So for example, we could replace all of the base Julia matrices and vectors with static arrays from the staticarrays.jl package. And what this does is it performs very efficient linear algebra by stack allocating small arrays rather than the default heap allocation. And so by just changing like 5 lines of code in our model definition, we can get a 5 times speed up essentially for free. We also have GPU implementations of these algorithms. We have a base default one using cuBLAS, which is the linear algebra framework that comes with NVIDIA's CUDA. We've also, so this framework isn't particularly specialized for this case of large batches of very small matrices. So we've actually written our own custom CUDA kernels, which are like right at the theoretical limits of what you can achieve with a GPU. And so overall, it's many orders of magnitude faster than the CPU. And there's no direct comparison we can make to another package because this is the first implementation. The closest thing would be a PyTorch package called torch-Kalman filter, KF. And so this performs batched Kalman filters, so that operation is a strict subset of the operations that take place when doing a Rao-Blackwise particle filter with a linear Gaussian submodel. And so even though it's doing less operations than the entire thing, our model is still more performant.
So the entire point of this module is essentially solving a single problem. It's getting the filtered states, or the filtered density, the posterior of the state space model. And so for analysis, we essentially designed a system of callbacks that the user is encouraged to implement by using like these distributional objects as like inputs to some callback. And so like for analysis, that's pretty much up to the user to define those. But we do include some of our own callbacks, such as efficient storage of like particle trajectories over time, which is a very cheap way of getting like a smooth distribution without doing a backwards pass of a filter or a sampling algorithm. Furthermore, we've designed a system of modular like resampling, where we not only designed our own very boilerplate resampling algorithms such as the stratified resampler, multinomial resampler, But we encourage the user to then define their own like algorithms, something a little more complicated, such as like a Metropolis resampler that can be parallelized over like a system of GPUs. Furthermore, something more interesting, or at least something that I find quite interesting, like a differentiable particle filter with use of like entropy regularized optimal transport. I've cited both of these papers, by the way, at the very end. But since we have like a very modular resampling system, we encourage users to do something like this. And it's very easy to do in general. And since I was talking about, differentiable particle filters, I'd like to talk a little bit about automatic differentiation within this interface. It's actually quite a bit difficult to do because of the recursive nature of sequential Monte Carlo. But currently, we do support forward mode automatic differentiation using forwarddiff.jl. And so some motivations as to why it would be useful for particle filters or Kalman filters in general. The low-hanging fruit here is maximum likelihood estimation. That's unfortunately everywhere in fields like macroeconomics and whatnot, stuff that I'm used to. But also, it adds a composability within Turing models. If we support some kind of automatic differentiation, we could then compose a filter within a Hamiltonian Monte Carlo. Furthermore, we could design our own filters like variational sequential Monte Carlo or other algorithms kind of akin to that.
Cool. So one other quick point that I'll brush over, and we can talk about more in the post session if anyone's interested, is that we have an extension to this framework which supports multiple target tracking with all the standard data association methods you would expect. And so we're soon going to be adding the ability to add and remove tracks that you're tracking. And at that point, it will have feature parity with StoneSuit, which is probably the most popular framework for multi-target tracking, except we would have the added bonuses of performance and a bit more of an elegant interface.
And lastly, just to present a little bit of that integration with Turing, since we mentioned it in the very beginning, we have a quick introduction to particle marginal metropolis Hastings with advanced MH. It's a very, very easy addition. Essentially, design your density function by calling that GeneralisedFilters.filter on the toy model. That toy model is a user-defined function that generates a state space given data parameters, where we set the algorithm to be any kind of filtering algorithm, like a Kalman filter, particle filter, Rao-Blackwell particle filter, and the data is self-explanatory. And we also have a working version of particle Gibbs as well, as some like MLE. But it's pretty composable stuff. It's very flexible, and it's very modular, and we're pretty proud of it. So yeah, I think that's it, right?
So we've got the references here. If you have any questions, please ask now, or we can chat in the post session.
Questions? Yeah, okay.
Thanks for the talk. In terms of integration with Turing, have you thought about how users who write their sort of state space model in the Turing probabilistic programming language can hook into this and specify that they want certain parts of the state to be represented with these specialized representations?
Go for it.
Yeah, so this is actually quite a difficult problem due to how Turing is architected. In a sense, it is not like you run through the entire model and can go, this is a state space model, I should dispatch this faster method. You're kind of running through the model on the fly. So I think the way we see it being used is probably as a nested model inside of Turing. So in that last example, for example, where we're using it inside of particle marginal metropolis Hastings, or within the Gibbs sampling abilities that Turing has. But in terms of just writing your model in Turing style DSL, probably not going to happen.
Yeah, it's kind of tough to infer the latent dynamics from a Turing model. There are a bunch of examples online where it's essentially just traversing a series of function calls. Since it's not like a graphical probabilistic programming language, there's really no easy way to do that.
Thank you.
Any other questions? Okay, Wantiez.
I was wondering to what extent the algorithm that you're presenting is new, and whether the correctness of that algorithm is obvious or needs to be proven carefully, So I guess the question is your contribution the careful implementation and making this actually usable, or is there actually a new algorithmic technique here?
Yeah, no, so these are standard algorithms that, yeah, you'll find them dotted around the place in literature, but it tends to be like, yeah, we've done our own hacky implementation for this one paper and, you know, not done a general purpose one. So yeah, what we're offering is a very general purpose implementation that can be used in wider settings, but also very performant implementation of it. Like we're really kind of focused on, like, you know, getting to that theoretical optimum of throughput. So that's probably the main contribution that we have.
And if I, as a layperson to SMC, want to learn about the correctness of this sort of technique, where should I look? Should I look at any of these sources?
Yeah, so I think I forget the name of the textbook.
An Introduction to Sequential Monte Carlo by Nicolas Chopin. Definitely highly recommend that one. Yeah. There are a bunch of others, but that's my favorite. Just for general, like, time series and stuff like that. Durbin and Koopman also have a very good book. Yeah, I don't know. Any others?
Yeah, I can't remember the names now, but I can perhaps try to after.
Yeah.
Thank you.
All right. Any questions? Okay, I had one question, but maybe I'm too unfamiliar with the Turing ecosystem. So how does this plug into Turing? Like, or does it make sense to even ask this question? Like, what's the API and how do they work together?
Yeah. So this is a bit of a confusing point that we've maybe glossed over a bit, in that I guess this kind of maybe sits next to Turing a bit, in that, so the way you would define a state space model with this is kind of independent to the normal Turing model that you would be doing. You're defining those three distributions: the initialize, the transition, and the observation. So it's more like, yeah, it lives as part of the general Turing ecosystem. We've made sure that it integrates as a higher level, as like a nested model, that if I want to take one of these models and use it within Turing in Gibbs sampling of particle Gibbs, or within Metropolis Hastings, maybe HMC once we have differentiable methods working, then yeah, that's kind of the connection between those, but it's not direct.
All right. Okay. Thank you.
Yeah, I'd kind of like to relate this to something like using like a PDE within Turing, right? You're not actually designing that, you know, partial differential equation in the Turing like model itself. Like, there's nothing in Turing that allows you to do that, and so you have to use something like ODE problems or whatever to define that, and then like compose that within Turing. And so that's essentially what we're proposing and what we're doing.
Okay, thank you very much. So if there are no questions, we can thank Tim and Charles one more time. And yeah, so